All right, today we're going to tackle a concept that is, no joke, physics' ultimate shortcut, the work-energy theorem. Get ready to see how one simple idea can totally change the way you look at motion.
I mean, what if you could just bypass some of the trickiest parts of Newton's laws? What if you could solve these really complex motion problems with just one single elegant equation? Well, that's the powerful promise of what we're talking about today.
Okay, so to get our heads around this shortcut, we first have to redefine a word we all think we know, work. Now, in physics, it has a very, very specific meaning, and it's probably not what you're imagining.
See, in physics, work is literally all about transferring energy. You apply a force, an object moves some distance, and boom, energy changes hands. But the secret sauce, the thing that changes everything, is that cosine of theta in the equation. It's all about the angle between where you're pushing and where the object is actually going.
So that angle, theta, that's what decides if you're putting energy in or taking it out. When the force helps the motion, like when you're lifting a book, your force is up and the book moves up. They're aligned. The angle is 0, cosine of 0 is 1, and you're doing positive work. You're adding energy to that book.
Okay, but now what if you lower that same book, but you do it slowly, with control? You're still applying an upward force to keep it from just dropping, but its displacement is downward. Your force and the motion are in total opposition. That's an angle of 180 degrees, and the cosine of 180 is -1. So you're doing negative work. You're actually taking energy away from the book's motion.
And then there's this one. This is the one that really trips people up. If you just carry that book horizontally, at a constant speed, you're pushing up on it to fight gravity, right? But the book is moving sideways. The force and the displacement are perpendicular, a 90-degree angle. And the cosine of 90 degrees? It's 0. So believe it or not, in the language of physics, you're doing exactly 0 work on that book. Yeah, even if your arms are on fire.
Okay, so work is energy transfer. Got it. But what's the payoff? Where does all that energy actually go when you do work on something? Well, that brings us to the energy of motion.
When you do work on an object, what you're really doing is changing its kinetic energy. This is the energy it has just because it's moving. The more mass it has or the faster it's going, the more kinetic energy it's got. And that formula, K equals 1/2 mv squared, yeah, you're going to want to remember that one.
The best way I've heard this explained is with a motion bank account. Just picture it. Kinetic energy is your account balance. Doing positive work on an object, that's a deposit. You increase the balance, it speeds up. Doing negative work, that's a withdrawal. You lower the balance, it slows down. Simple as that.
All right, so we've got our 2 key ingredients, right? Work is the energy transfer, the deposits and withdrawals. And kinetic energy is the energy of motion, the account balance. It is time to put them together and reveal this awesome shortcut.
And here it is, the main event, the work-energy theorem. It's so simple, but so powerful. It just says that the total or net work you do on an object is exactly equal to the change in its kinetic energy. W net equals K final minus K initial. It's this beautiful direct link between all the pushes and pulls on an object and how its speed changes because of it.
And look, don't just take my word for how powerful this is. The OpenStax textbook puts it perfectly when they say that this theorem makes some calculations way simpler than trying to grind through Newton's second law. Instead of tracking every little acceleration, you just look at the beginning and the end. That's the shortcut.
So really, it boils down to this super simple but powerful idea. If you see something speed up, you know for a fact that positive net work was done on it. Period. If you see it slow down, the net work had to be negative. It's a direct cause and effect.
Okay, theory is great, right? But how does this actually play out in the real world? Let's take a look at the theorem in action, with everything from stretchy springs to massive spinning flywheels.
So this theorem works great if you're just pushing something with a constant force. But what happens when the force isn't constant? Like a spring, the more you pull on it, the harder it pulls back. How do you deal with that?
Well, that's governed by something called Hooke's law. Basically, the force from the spring is proportional to how far you stretch it. That little K is just its stiffness, and that little negative sign, that's actually super important. It just means the spring is always trying to get back to where it started. It wants to restore itself. So how on earth do we calculate the work when the force is changing all the time? Well, this is where a little visual trick comes in handy. The work done is just the area under the force versus displacement graph. For a spring, that's a triangle. No crazy calculus needed. Just finding the area of a triangle. How cool is that?
And get this amazing shortcut isn't just for things moving in a straight line. Nope, it works just as perfectly for things that are spinning. The idea is identical. The net rotational work, which comes from torques, equals the change in rotational kinetic energy.
Just look at this table for a second. The parallels are incredible. It's like rotational motion is the long-lost twin of linear motion. Force becomes torque. Mass becomes something called moment of inertia. But the structure for work and kinetic energy, it's exactly the same. Physics gives us this amazing, consistent way to describe all kinds of motion.
Okay, so let's zoom out for a second. We've got this great tool, but where does it fit in the big grand picture of physics? Well, it's actually a stepping stone to one of the most fundamental laws in the entire universe, the conservation of energy.
So you might be wondering, what's the real difference here? Well, think of it like this. The work-energy theorem is all about how external forces from outside a system come in and change its energy. The law of conservation of energy, on the other hand, is for isolated systems. It says that if nothing from the outside messes with it, the total energy inside stays constant. It might change forms, like from potential to kinetic, but the total amount is locked in. And that right there is the key relationship. The work-energy theorem isn't some separate competing rule. It's really just a powerful, specific way to use the universal law of conservation of energy, especially for systems that aren't isolated, when those outside forces are doing work.
All right, let's wrap this all up. What are the big things you should walk away with? 1. Work in physics means force applied over a distance. 2. The net work you do directly changes an object's kinetic energy, its energy of motion. 3. This whole theorem is a massive shortcut for solving tricky problems. And 4. It's incredibly versatile. It works for straight lines, for spinning things, and even for forces that change.
And I want to leave you with one last question to mull over. We've defined work as energy transfer. And we all know friction does negative work. It slows things down, right? So that energy is removed from the object's motion. But energy can't just disappear. So where does it go?